Yep, good.
Yes.
Great. All right. So I guess first of all, I'd just like to say, thank you for having me in your microeconomic theory seminar. I'm really more of an experimentalist than a theorist, but I have a theory paper here, so I'll present it to you guys. I've been very impressed with the lineup of speakers you've got so far. So hopefully I can live up to what's come before. And as Alex said, I'm going to be talking about preference randomization in games with ambiguity averse agents. Okay, so the kind of underlying motivation here is to recognize that agents always have the option to randomize. Okay? And particularly if you're an ambiguity averse agent, you may have a strict preference to randomize. Okay? Now, this is well known in the decision theory literature. I'm going to try to port some of these ideas from decision theory across into game theory. And one of the things here is that these randomizations in a game are often unobservable. If I'm an observer of a game, I'll often just see the pure strategy realization of a mixed strategy. And so I'm interested in thinking about what are the observable fingerprints of these unobservable randomizations. If I'm watching a game, and for me in particular, if I'm running a game theory experiment, how can I tell whether my subjects are randomizing or just playing a pure strategy? And what are the observable implications of their preference or randomization? So there's a little bit of a kind of contradiction in the literature between the theory side of things and some of the previous experimental results. And part of my motivation is trying to resolve this, this apparent contradiction. So on the theory side, for games with ambiguity averse agents, there's a few results out there. Chen and Liu is kind of the most applicable to my current setup, that establish that an ambiguity averse agent is going to be indistinguishable from an expected utility agent. And in particular, the set of rationalizable strategies for an ambiguity averse agent and an expected utility agent will be the same. And yet we have experimental evidence that ambiguity averse subjects play differently in games than expected utility subjects. And in particular, they often play strategies that are not rationalizable for an expected utility subject. So these two results don't mesh. And part of what I'm trying to do is to try to reconcile these. Okay, so there's a lot of different reasons why you might want to randomize, okay, why people might randomize. Today, the focus is going to be on randomization to build a hedge against ambiguity. Okay. And the underlying idea goes back to at least Rafer in 1961 and has been explored a lot recently in the decision theory literature, of the idea being that if I flip a coin, I can use the outcome of the coin toss to hedge against any ambiguity that I might experience. And effectively, you're converting ambiguity to risk by conditioning on the toss of the coin. Okay. And so by doing this in a game, you can use a mixed strategy to build a hedge against strategic uncertainty, against the uncertainty you face about the behavior of your opponent. Okay. So as an example of how this might apply to games, consider a simultaneous matching pennies game where one player must place a penny covered by their hand on a table before the other player. Okay, so this is the type of situation you might give to a undergraduate game theory class and ask them, is this a simultaneous or a sequential game? Okay, the physicality of it, the agents are moving one at a time, but from a game theorist point of view, this is a simultaneous game. So one player puts the penny down on the table covered by their hand, and then the other person does the same thing. Okay? So think about what happens if my opponent places their penny first. So my opponent has their penny down on the table. I can get my penny, I can flip it in the air and just play whatever the toss comes up. Okay? And in this case, I'm going to build a hedge against the ambiguity I experienced about my opponent's decision. Okay? And the reason for this, and this is exactly Rafer's argument, is that if my opponent has played heads, then when I flip my coin, I'm going to win 50% of the time. And if my opponent has played tails, when I flip my coin, I'm going to win 50% of the time. So I've converted the uncertainty about my opponent's strategy into risk. Okay. Now, on the other hand, let's think about the case where you place the penny first, okay, and think about your intermediate stage utility here. Your randomization does not necessarily provide a hedge in this case. Okay. If I flip a coin, I put it down first, okay, if my mix comes up heads, well then at that intermediate stage after I've played the coin, I'm still exposed to ambiguity about my opponent's decision. I don't know what my opponent's going to do. They might play heads or tails. That is an ambiguous event for me. And so I'm exposed to that ambiguity. And similarly, if my flip comes up tails. Okay. Now, in more realistic settings, we can think about which scenario is true as being a subjective belief of the agent. Okay. What is the agent's subjective belief that their mix builds a hedge against ambiguity? Okay. And the ideas in this slide are really an application of the model of Kota Saito or Kei and Zhang to a game, and I'll get into a little more detail of that later. But the underlying idea is that your preference randomization is going to be stronger the more likely you subjectively believe case one is true. Okay. So that's a little bit of the motivation, but the kind of the key research question here that I'm going to answer is, how does your preference randomization affect the set of rationalizable strategies? Okay. And the answer is quite straightforward. And it's that the set of rationalizable strategies is going to expand as your preference randomization weakens. Okay. So another way to think about it, as I think that case two becomes more likely, my set of rationalizable strategies will expand. And the rough intuition here is that as your preference to randomization strengthens, more strategies are dominated by mixes, and therefore the set of justifiable and rationalizable strategies is going to shrink. Okay. Now there's kind of an inverse intuition you might have that turns out not to be true. And this false intuition is that you might believe that as preference randomization strengthens, more strategies would become justifiable as a part of mixed strategies. Now, I have a preference to mixing, so maybe more things become useful to me to help me hedge against uncertainty. And the reason this fails is actually somewhat instructive. If you were to fix your beliefs, then the intuition in this bullet point here, I'll just kind of draw on that. If you were to fix beliefs, the intuition in this bullet point would be true. Okay. As your preference randomization strengthens, you might be able to bring in some other mixed strategies to build a hedge. But it turns out that those other mixed strategies you bring in will already be best responses to some other belief. And so it doesn't affect the set of justifiable strategies.
Evan, can I ask a very simple clarifying question? So you use both the terminology of rationalizable and justifiable. So are they the same? Or what do you mean by justifiable?
Okay, yeah, so I'm going to get to the formal definitions later on, but just to give a preview, you think of justifiable as being the set of strategies that are a best response to some belief of mine, and rationalizable as the iterated elimination of all strategies that are not best responses. Okay.
So we can justifiable means one round, and rationalizable means like multiple rounds.
Yeah,
yeah. Okay, got it. Yeah, thanks.
Yeah, I'll give a more formal definition later that is a little bit different from that, but the intuition is exactly that. So given, and the other kind of side of my research question here, being an experimentalist, I want to think about, well, okay, if I see some data on people's behavior in a game, can I back out of that? What must their strength of preference for randomization have been? Okay. And the answer is that we can find an upper bound on their strength of preference for randomization from their behavior in a game. And I'll go through a couple of examples and show how that works out. All right, so I guess I've got an example we'll go through in just a second, but now might be a decent time for any questions, if anyone has any questions from the kind of motivation part there. No. Okay, so I'll give an example to show how preference randomization can affect the set of justifiable and or rationalizable strategies. So this is a modified battle of the sexes game. Okay, if we just had strategies R and C, it would be a standard battle of the sexes. But I've added in this strategy P that provides a fixed but low payoff. If you want to tie it back to the old story of Battle of the Sexes and that you've arranged to go on a date with someone, you can't remember which location the date is at. We have mobile phones now. So P for phone, you can call them and ask, okay? But it's a bit embarrassing that you forgot where the date's going to be, so that's why the payoff is low. Okay. Now, let's assume that agents have maximum expected utility preferences. Okay, so this is the way I'm going to model ambiguity aversion throughout this. So we're going to have maximum expected utility. Okay, and really what we have here, this is just expected utility here. You have your belief multiplied by the utility of the outcome. Okay, for now, we can just think of these payoffs as all being utilities in the standard game theory sense. When we get to talking about how observable things are, we'll need to think about risk aversion as well, but for now we can just think about these payoffs are utilities. And then, consistent with the MEU model, you're going to have some set of possible beliefs that you think your opponent might play, and your utility will be the worst case out of that set. Okay, so it's a minimum of your expected utilities over the set of beliefs that you have. Okay? And the notation is reasonably standard here, I think. Okay, so let's think about what happens. What happens if I do not have a preference for randomization? Okay, so we can think if I'm in case 2 from the matching pennies example. Okay, well, in that case, my utility of a mixed strategy is just going to be the linear combination of my utility of the underlying pure strategies. Okay, so when you have no preference for randomization, mixed strategies are just a linear combination of the underlying pure strategies. Okay? Now, in this case, for Rowena, the rogue player, all strategies are going to be justifiable for her. Okay? If she believes her opponent is going to play R, then her best response is clearly to play R. Okay? If she believes her opponent is going to play C, her best response is to play C. And if she has complete uncertainty, okay, so here her belief set is that her opponent could do anything, okay, then applying the maximum expected utility, her payoff from playing R, well, she's concerned her opponent will play C and she earns 0, so utility from R is 0. If she plays C, the minimizing case is her opponent plays R and she receives 0, so her utility from C is also 0. But the utility from playing P, well, that is just X, okay? And X is assumed to be bigger than 0. Okay, so in the case of complete uncertainty, her best response is P. So we can justify any of Rowena's pure strategies as a best response to some beliefs. Now let's think about the case where the agent has a strong preference for randomization. So this is case 1. I'm a Rafer 1961 type person. I believe that randomization will build a hedge against strategic ambiguity. And in this case, the utility of my mixed strategy is calculated by finding the expected utility of the mixed strategy and then taking the minimization over that, okay? So kind of you flip the order of operations. So in this case, the strategy P is going to be dominated by this mix of 1/3 R plus 2/3 C, okay? And the reason for this, well, if I play P, that gives X for any possible beliefs. Okay? if I play this mixed strategy, that's going to give me a utility of 2 for any possible beliefs. Okay, because if I believe my opponent's going to play R, well, I have 1/3 times 6 plus 2/3 times 0, which is 2. If I believe my opponent's playing P, well, I have 2. And if I believe my opponent's C, I get 2/3 times 3, which is also 2. Okay, so this part of the expression evaluates to 2 for any belief about my opponent, and therefore the utility is 2 for all beliefs. So we have a case here where when Rowena has no preference for mixing, her rationalizable set is RP and C. Or, well, establish a justifiable set of strategies as RP and C. But when Rowena has a strong preference for randomization, her justifiable set is only R and C and not P. Okay, so kind of this example just immediately shows that preference randomization will play a role here somehow. Okay, and hopefully it's provided a little bit of motivation as to how that mechanism works. Okay, so now I'm going to talk a little bit about Saito's model of preferences for randomization, because essentially I'm going to pick up his model and port it across into a game. Okay. So Saito axiomatizes his model of preferences for randomization as a hedge against ambiguity. And I'm not going to give the axiomatization here, but there is one, and it is reasonable. His model essentially takes the utility of the case where I have a preference for randomization and the utility of the case where I do not have a preference for randomization, and just takes a linear combination of those two things. And that linear combination is modulated by this parameter delta. Okay, so this is just what we had before. This is my preference for a mixed strategy when I have a preference for randomization here, and here is your preference for randomization. Well, sorry, your utility of a strategy when I don't have a preference for randomization comes in here. So as delta is higher, as delta goes to 1, I have a strong preference for randomization. As delta goes to 0, I have a weak preference for randomization. And this is the model we're going to take. And that's what when I say an agent has a stronger preference for randomization, what I mean is they have a higher value of delta in the Saito model. Just a little bit of notation. So the set of beliefs for player I is given by the capital phi, and it's a subset of the set of mixed strategies of their opponent. And we're also going to need later on the set of all sets of beliefs, and that's going to be this calligraphy P. Okay, so now I'm going to outline the main result, and then I'll talk about some implications of it. I may not get through all of these points. We'll see how we go with time. Okay, so we're going to need to start with a few definitions. Okay, and we'll get to the definitions of justifiability, rationalizability, but the first thing we need to think about is dominance. Okay, and it turns out dominance in this model with the Saito model doesn't quite work in exactly the same way as dominance in the expected utility case. Okay, so we can say a strategy is dominated if for all beliefs the utility of this sigma prime is greater than the utility of sigma. And that's kind of the standard definition of dominance. Okay, now given this definition, we're going to illustrate with this example kind of where things don't quite work as you might expect in this model. So here's a game where I'm just showing the row player payoffs. Okay, we're going to just suppress the column player payoffs. We're going to think about the role of dominance in this example game. Okay. So when delta is bigger than a half, so when my preference for randomization is strong enough, then strategy A is dominated by the mix of a half B and a half C. Okay. Clearly, when my opponent plays Z, B and C outperform A. When we're thinking about X and Y, you can see that mixing B and C provides a good outcome on average, which means that when my preference for randomization is high, if delta is 1, it would pay on average 20 across each of these two states. And A only pays 10. So when delta is high, A is dominated by a half B, a half C. So now what I'm going to do is I'm just going to show you a graph of the utility of some various strategies as a function of delta on the x-axis and utility on the y-axis. So first of all, I just laid out the utility of A, and this is under an assumption that I believe that my opponent will play anything. So I have full uncertainty about my opponent's strategy. Okay, so I'm just taking now one particular belief, that belief of pure uncertainty, and showing you the utilities for that. So A, the worst case scenario for me if I play A is I get 10, so my utility of A is 10. D, my worst case scenario if I play D is 0, so my utility there is 0. And these are independent of delta, okay? Because delta is a preference randomization. The utility of any pure strategy is independent of delta. And here now is the strategy B plus C on 2. Okay? So we know that the strategy, the green strategy, dominates A when delta is bigger than a half. So the utility must be higher for all beliefs. And so it is here. Okay? But now look at this strategy. This is 80/89ths of the time I'm going to play A, and 9/89ths of the time I'm going to play D. And this strategy actually outperforms B plus C over 2 for some range of delta. Okay. In particular, delta of 0.6, this strategy is a best response to complete uncertainty. Okay. And what we have here is that a dominated strategy, which is A, is still being used as a component of a best response. Okay. So despite A being dominated, it's still useful for this particular set of beliefs as a hedge against the uncertainty of my opponent. Okay. So here, in an expected utility case, if a pure strategy is dominated, all mixes that use that pure strategy are also dominated. Here, that's not true. Okay, so I'm going to need a stronger definition of dominance. Okay, so and I'm going to call this total dominance. I couldn't find any similar definitions in the literature where I could borrow the name from, so I had to come up with something. Hopefully, I think this makes some sense. So we're going to say a strategy AI is totally dominated if every mixed strategy that uses AI is dominated. So in the expected utility case, dominance and total dominance are completely equivalent, but here they are not. Okay? So we're going to use this stronger notion of dominance. Okay. So one implication of this is that our definition of rationalizability is going to be, we need to think carefully about what it's going to be. Okay, there's at least 3 possible distinctions. I'm going to define what I mean by reasonably in a minute, but there's 3 conceptual ways you could think about the set of rationalizable strategies. Okay, it could be the set of pure strategies that could reasonably be played in a game. Okay? We could think of it as a set of mixed strategies that can reasonably be played, or the support of the set of mixed strategies that can reasonably be played. Conceptually, these are all ways we could define a notion of rationalizability. Okay? Now, if we have standard EU preferences, well, 1 and 3 are the same, and if you know 1 or 3, then you can figure out 2 immediately, because all mixes would be fine as well. But here, these are not equivalent. Okay, so we need to kind of pick which one we're going to go with. We're going to go with number 3. Okay, and the reason for this is the underlying intuition of why we want a notion of rationalizability is, I think that if we have an outside observer watching a game, we want to ask, well, what things might that observer see? Okay, if we use 1, the observer might see a pure strategy realization that they believe is not rationalizable or not reasonable, but is in the support of the mixed strategies that can be reasonably played. So it would be not appropriate. And if we take the view that we can't observe a mixed strategy, well, we rule out 2. And so the only sensible way to go is to use definition 3. Okay, so that's what we're going to do for rationalizability. So we're going to build up our definition of rationalizability iteratively. Okay, and we're going to start with justifiability. This is a more formal answer to your question from before, John Tao. So we're going to let this set be my set of mixed strategies that are a best response to these beliefs, phi. Okay? And then this set is going to be the union over all my possible beliefs. And so this is a set of strategies that are a best response to something. Okay? And we're going to say that a strategy is justifiable with respect to particular beliefs if the strategy AI is in the support of this top one. And we're going to say that a strategy AI is justifiable if it's in the support of this thing. Okay. So that's our notion of justifiability. And then we can construct the set of rationalizable strategies recursively. Okay. So we'll take the first step to be the set of justifiable strategies. Okay. Then we need to construct the set of beliefs I might hold about my opponent when I assume my opponent is only going to use a justifiable strategy. Okay. So this is the set of essentially all closed and convex subsets of the set of mixed strategies my opponent might use. And then we iterate to my next level set of best responses of being the union only considering belief sets that are inside this set we defined in number 2. Okay. And then the set of rationalizable strategies, we take the intersection of all these sets going from n to infinity. Okay, so it's analogous to the kind of standard definition of rationalizability, but we have to be a little careful in how we're constructing our set of beliefs here in step 2. Okay. So this is our set of rationalizable strategies. Okay. So this set of rationalizable strategies I've defined here is, as you might expect, closely related to some previous notions of rationalizability that are in the literature. For example, if delta is equal to 1, then the set of rationalizability I just defined is equivalent to the standard Peirce-Bernheim. Well, sorry, it's equivalent to the correlated rationalizability. Okay? I've got a correlated notion here because I'm not imposing the independence of the beliefs in this set. So I have a correlated notion of rationalizability. And so if delta is equal to 1, it's actually equivalent to correlated rationalizability for a subjective expected utility agent. Okay? And this result is essentially the Chen and Liu result. The proof is very simple, so I'll give it. So suppose that I have for any set of beliefs, this strategy sigma star is my best response, and let phi star be the corresponding utility minimizing belief. Okay? Then sigma star is also the best response for an expected utility agent who has the same belief. Okay? So if a strategy is justifiable for one of my Cyto agents with a delta equals 1, then it's justifiable for an expected utility agent. And conversely, suppose that sigma double star is a best response for an expected utility agent with these beliefs. Well, then I can let my belief set be that singleton, and the sigma double star is also a best response in the Cyto sense when delta equals 1. So there's an equivalence of the best responses here for delta equals 1 with an expected utility agent. The case of delta equals 0 also appears in the prior literature in this paper from Epstein in 1997. And I'm not going to give a proof there because all you need to do is just kind of write down the definitions and stare at them and they're equivalent. Okay, so the two endpoints have been covered before in the literature, and really one of the things I'm doing is I'm filling in the gap of what happens in between when delta is between 0 and 1. Okay, when we have a partial preference randomization, if you want to think about it that way. Okay, so I'm going to show you two lemmas before I establish my result. And the first lemma, and kind of the most important one, is essentially a lemma from Peirce's paper. Versions of it go back to Wald as well. His complete class theorem is essentially the same idea. And so Peirce establishes the equivalence of undominated and justifiable strategies for expected utility agents. Okay, if a strategy is undominated, it must be justifiable for some beliefs. Okay. Now, we've already seen an example where this fails for the cyto preferences that I'm studying. Okay. But we can recover the result using the stronger notion of total dominance. Okay. So my version of Peirce's lemma is that a pure strategy AI is totally dominated if and only if it is not justifiable. So this is the equivalent result for the cyto preference structure. And the proof for this is very beautiful, so I'll take you through it. Many of you have probably seen it before, but it's a nice proof, so we'll go through it. So the if part is straightforward. Okay, it's just straight from the definitions. If AI is totally dominated, then all of its mixes are dominated, and therefore none of its mixes can be a best response, and by definition, it's not justifiable. Okay? The only if part is the nice part of the proof. Okay, so we're going to suppose that strategy AI is not justifiable. Okay, we're going to use a saddle point kind of argument. So this means that for every mixed strategy that uses the strategy AI with a positive probability, there's going to exist a function that maps from my beliefs into my strategies such that this function will pick a strategy that gives me a higher payoff than the mixed strategy. Okay? This is just an implication of the fact that AI is not justifiable. Okay? So for any mix, we can always find a better response, okay, is what we've done here. And this is a better response function. Okay. Now we're going to construct a zero-sum game. Okay. And the way to think about this zero-sum game is that the player in question, player I here, is going to be picking one of their strategies. And we're going to construct them playing a zero-sum game against player 2 who picks their belief. Okay? So constructing a game where I pick a strategy and you pick the belief that I must hold. Okay? That's the interpretation of this game. And we're going to set the payoffs of this game in such a way that we're going to normalize my payoffs so that whenever I play this mixed strategy that we're considering, my payoff will be 0. Okay? I'm going to just normalize so my payoff is 0 whenever I play this mixed strategy in question. And your payoff is the negative of my payoff. So you're picking my beliefs to minimize my utility. I'm picking a strategy to maximize my utility. Okay, we can go back into the mathematics literature and find the minimax theorem in pure strategies holds in this game. Okay. I won't go into the details here, but we can establish all the necessary conditions for this theorem from Sion. And so what this means is that there must exist a Nash equilibrium of this game. Okay, so there exists a Nash equilibrium. We're going to denote it by S1 star, S2 star. And now for any strategy that you play, any belief set you choose from me, my utility from playing my Nash equilibrium strategy here is going to be at least as large as the utility I would receive in the equilibrium, okay, because this is a zero-sum game. Okay. That is going to be at least as large as if I played the better response to your equilibrium strategy. okay, by definition of the better response function, and the Nash equilibrium must be best response. And this is strictly greater than if I played the strategy we have in question, okay, from the definition of the better response function. And by the construction of this game, my utility from playing this sigma AI strategy is 0. Okay? So the utility of my Nash strategy is always strictly greater than 0, no matter what belief set you choose for me. Okay? And so this tells me that this strategy here is dominated by my Nash strategy. Okay, so we suppose that AI is not justifiable, and this holds for every mixed strategy that uses AI with a positive probability. Every mixed strategy is dominated. Okay, so we've established dominance here, and this dominance goes through for the original utility function. Okay? And so if AI is not justifiable, then it is totally dominated. Okay? All right, so that's the Peirce lemma. The other lemma I'm going to need is a dominance lemma. Okay, so we're going to establish monotonicity of dominance. Okay, and so we're going to say that for all delta primes less than delta, if sigma prime dominates sigma at delta prime, then it also dominates at delta. Okay. And so the proof here is reasonably simple as well. So we're going to, for the first part is we need to prove that sigma prime dominates sigma at delta equals 1. Okay, so we assume that it dominates at delta prime, and we're going to show it dominates also at delta equals 1. Okay? And we do this by using the singleton belief method, same as we proved for the expected utility proof a couple of proofs ago. So writing this to be our utility minimizing belief of sigma prime, we're going to have the following expression at delta equals 1. Okay, my utility when I have some belief set phi I is equal to my utility if I just believe the minimum, the worst case belief. This is also going to hold if we go from delta equals 1 to delta prime, because when my belief is a singleton, my utility is linear, is constant in delta. Okay? There's no way for me to use a mixed strategy to build a hedge here because I only have one belief. And so these are equivalent. This is bigger than my utility from playing sigma from the assumption that it's dominated. We can then go back to delta of 1 because again, utility of when you have a singleton belief is constant in delta. And this must be bigger than or equal to my utility with respect to the initial belief set. Okay, so we assume that it's dominated at delta prime, and we can show that for every belief set phi I, this holds, so it's also dominated there. And then utility is linear in delta. Okay, that's just from construction of the utility function. So if I've established that we're dominated at delta prime and we're dominated at 1, we must be dominated for all deltas in between. Right. Okay, so now the main theorem. Okay, this is kind of the key result here of the talk, is that suppose that delta is bigger than or equal to delta prime. If a strategy AI is justifiable at delta, then it is also justifiable at delta prime. Okay. And the proof is very, very simple, given the two lemmas we've just established. So suppose that A is contrapositive, suppose that AI is not justifiable at delta prime, okay. Then we use Peirce's lemma to move into the dominance realm. It must be totally dominated at delta prime by Peirce's lemma. Then a dominance lemma tells us that we have monotonicity in the dominance definition. And so AI is totally dominated at delta. And then we can use Peirce's lemma to go back to justifiability. Okay? So really the idea here is that we're using Peirce's lemma to shift from justifiability to dominance Monotonicity and dominance is easy to establish, and then we can go back via Peirce's lemma again. And as a corollary, suppose that delta is bigger than or equal to delta prime, then the set of rationalizable strategies will satisfy this set inclusion. Okay? That just comes from iteratively applying the definition of rationalizability like we had before. Okay, so I kind of chewed through a kind of lemma proof there for a bit. So this might be a good point to stop and ask if there's any questions before we kind of get into looking at, you know, some kind of the observability of the model parameters and how the model might work if we're trying to take it to data or something. All right, so we'll get right into talking about the observability of the model parameters. Now, the basic kind of implications here are very straightforward, right? If a strategy is justifiable for all deltas, you know, less than some threshold, but not justifiable above that threshold, well then, if I see you play that strategy, it must be that your preference randomization is below the threshold. Okay? Now, the kind of the caveat here is that we're assuming rationality, and in particular here, what I mean by assuming rationality is assuming you're rational with respect to the cyto preferences. Okay? So it's an assumption that you have these cyto preferences. If that is true, then I see you play AI, I know your preference parameter, preference randomization must be below the threshold. Okay? And similarly, you know, if there's some cutoff at which AI prime is rationalizable below the cutoff but not above the cutoff, and I see you play AI prime, well then if I assume rationality and common knowledge of rationality, okay, and kind of in the traditional kind of game theory sense, then we can conclude that again, your preference for randomization must be below the threshold. Okay, so this is, you know, is a straightforward implication of the way that the set of justifiable and rationalizable strategies is going to expand as my preference randomization drops. Okay. There is going to be some complications that come in from risk aversion when we start looking at the data, but we'll get to that in just a second. Okay. Now, previous experimental results seem to suggest that at least 30% of the population have a delta less than 1. Okay, so yeah, I view this as being evidence that, you know, this theory is, you know, empirically important in some way. Okay, the kind of default kind of, you know, say if you're Rafer, you would argue that everyone should have delta equal to 1. Okay, and we have empirical evidence that that's not true. So it justifies spending time thinking about what happens when people do not have delta equals to 1. Okay. Now, one thing that comes from this is kind of essentially, you know, a lower bound of the number of people who have a delta less than 1, because, you know, if a strategy is justifiable at delta equals 1, then I don't learn anything about observing you play that strategy. Okay. So the observation of behavior that is consistent with expected utility doesn't tell me anything about your preference or rationalizability. If we think back to the battle of the sexes situation, you know, if I believe you're going to play R with probability 1, well, I'm going to play R as my best response to that, and that doesn't tell me anything about your preference randomization. Okay? So, given that all we can observe is the realization of your mixed strategy, we can get a lower bound on the proportion of people who have a delta less than 1. Okay? And it's at least 30%, looking at a couple of the past experimental papers. Okay, so I'm going to justify my claims there. This is from my own paper. In this paper, basically all I did was I measured people's risk preferences, I measured people's ambiguity preferences, and then I had them play this game. Okay, and this game, the way to think about it is that if I am the row player, I essentially can place a bet on my opponent's behavior. Okay, if I think my opponent's going to play X, I can play A. If I think my opponent's going to play Y, I can play B, or I can take a safe option and just take 18 for sure if I don't want to take on that bet. Okay. The column player, you can think about, the column player essentially is trying to place a bet, and I just realized there's a typo here. That's actually a 22. It's not going to make any difference to what I'm going to say here. The column player is essentially placing a bet that do I think the row player is going to try to guess what I'm going to do, or do I think the row player is going to take the safe strategy? Okay. Now, if we assume risk neutrality, then this strategy C, and I'll relax this assumption in a minute, but for now, assume risk neutrality, the strategy C is justifiable if and only if delta is less than 8/11. Okay. I won't give you the calculations, but the intuition is that if delta is equal to 1, well, then I can mix a half A, a half B, and that will pay me on average, what is it? Like 19.5. And that's better than playing C, which gets me 18. So if I have a strong enough preference for randomization, a half A, a half B dominates C. But as my preference for randomization drops beneath some threshold, it turns out to be 8/11, then C becomes justifiable for me. Okay. Now, in these parentheses, I've put the proportion of subjects that I observed playing each of these strategies. We have 28% of people play C. Okay. So therefore, if I assume my subjects have these cyto preferences, they're rational with respect to cyto's preferences, at least 28% of them have a delta less than 8/11. Okay. I won't go through it, but we can also establish that B is rationalizable if and only if, it's iterated elimination argument, delta is less than 8/11. And so assuming rationality and common knowledge of rationality, at least 37% of subjects have delta less than 8/11. So stronger assumption, but tighter bound. Okay. Now, what about risk preferences? Okay. Tillman-Borges has already kind of addressed this on my behalf a long time ago. So suppose that you observe the outcome of a game with EU agents, but you don't know their risk preferences. Okay. What's the set of strategies that I might observe? Okay. The Borges set of rationalizable strategies, I'll call this B. Okay. And it turns out that in all games where strict dominance and weak dominance coincide, that this Borges set of rationalizable strategies is larger than my set of rationalizable strategies. Okay, what this implies is that unless I make some additional assumptions or have some additional knowledge about the risk preferences of my agents, then I can't really say anything. Okay. I'll skip the proof. So fortunately, in my paper, I have a measure of risk preferences, so I can get around this a little bit. Okay, so here on the x-axis, I've got risk preferences. On the y-axis, I've got preference for randomization. And here I've just mapped out the set of rationalizable strategies in each case. Okay, and we can see that, and one of the things I know in my paper is, are the subjects' risk preferences to the left or to the right of this line? Okay, so we can just focus, we can just strip away the data and just look at people whose risk preferences are to the left of this line. Okay, and we have for those subjects, 70% of those subjects play A. Okay, and that tells us that 30% of subjects must be in this region here. Okay. And so we have these 30% of subjects whose value of delta, they must be below this line, it's bounded away from 1. Similarly, there's a paper from David Kelsey and Sarah LaRue that does a very similar thing to my paper. They use a variation of the Battle of the Sexes game with a safe strategy. In their case, R is dominated by a mix whenever delta is greater than 4/5. And they see 30% of people playing R, we can conclude that at least 30% of subjects have delta less than 4/5. Okay, this is the same number as we had before, which is a little remarkable. If we're concerned that risk preferences might cause a problem, well, they'd need to have a CRRA parameter of greater than 2.2 to justify this just based off their risk preferences. So, and that's that's completely absurd. 1 is log utility. That just, so it's not risk preferences here in their particular game, given the parameters they have. All right, so I've got a few minutes left. Extensions. We could replace the MEU preferences with smooth ambiguity aversion. The caveat is it must be aversion here. The result would not go through if we allow for smooth ambiguity with ambiguity seeking preferences. But as long as we restrict it to be ambiguity aversion, it would still go through if we use the smooth ambiguity preferences of Klibanov, Marinacci, and Mukherjee. So that's nice. I conjecture the results would extend to the double MEU model of K and Zhang, but I don't have the proof for that. You need to bring in filtrations, and the proof technique would need to be very different. So I don't have the full proof, but I conjecture that also holds. This is what I want to talk about a little bit in the time that I've got left, is the relationship to some other rationalizability results in the literature. Okay, so it's worth pointing out that that Weinstein established that, I'm just going to use Z as a placeholder here for the set of rationalizable strategies in each case, that Z increases as risk aversion increases. Okay, so you can think about, the Borges set was very large, and that the set of possible strategies you could play expands as your risk preferences gets bigger. Okay. These authors established that the set of rationalizable strategies increases as ambiguity aversion increases. Okay. So what I have here is kind of a complementary result to these, that I've shown that the set of rationalizable strategies increases as your preferences to randomization decreases. Okay, so it's kind of a third dimension in which we have a monotonicity result. And particularly the relationship here to the Badagali et al. Paper, you can think about as your preference for randomization decreases, your ambiguity preferences get expressed more. Okay? In some rough sense, if I have a very strong preference for randomization, my ambiguity preferences are hidden by the fact I can randomize and cover them up, okay, to an outside observer. And so as my preference for randomization drops, the observable degree of ambiguity aversion increases. And so it's kind of natural that we both see similar monotonicity results. Okay. Now, if you compare bullet points 2 and 3, they're contradictory. Chen and Liu established that rationalizability is independent of ambiguity preferences. Okay, so that there must be some differences in their underlying assumptions here. And in the language of this paper, Chen and Liu assumed delta equals 1, while Badagali et al., they essentially assumed delta equals 1 for some strategies, but delta equals 0 for others. Okay, they argue that any strategy which could provide you a hedge, you should write into the strategies of the game. For those strategies, you can hedge against ambiguity. Anything that's not given to you as an explicit mixed strategy, they assume delta equals 0. I've already covered that result. The Borges result I gave before does depend critically on the weak dominance and strict dominance diverging. Okay, in the case where they're the same, so in the case where they're they're not diverging. If weak dominance and strict dominance do diverge, so that happens if there's the same payoff across multiple strategies that can occur, then there are examples where the Borges set is smaller than my set. And just in the last couple of minutes, I might quickly say there's some equilibrium comparative statics as well that from Hanani, Klibanov, and Mukherjee. and they discuss how things change if priors are fixed or if priors are allowed to vary. And the intuition there is very similar to my initial example where I held your beliefs fixed. Okay, if you hold the amount of ambiguity aversion fixed, then you no longer get your monotonicity results. But if you allow the ambiguity beliefs to vary fully, then you can get some nice monotonicity results, and they have the same thing in equilibrium. All right, so I'll just give a quick conclusion, and then I'll be happy to take any questions. I see there's one in the chat, I think, but maybe we'll hold on from that till the end. It's just JC saying he's headed off. All right, so what did I do? Well, I applied a model of ambiguity aversion and preference randomization to games. I picked up Saito's model and applied it to games. Using that, I was able to establish that the set of rationalizable strategies increases as your preference for randomization decreases. There is a substantial minority of subjects, at least 30%, who exhibit behavior that cannot be explained by risk preferences and is incompatible with delta equals 1. Okay. And so this indicates its heterogeneity in preferences randomization amongst the population. Okay, and we've seen this in a few other settings recently. I guess Marina Agronov and Pietro Ortoliva's paper is probably the main one that people might know. But that there is this building evidence that there are heterogeneity in preferences to randomization across various environments. And to leave you with something to think about, I'm not sure we really understand why this is the case at this point. So for me, I think that is a very interesting unanswered question, both from the empirical side and also from the theoretical side. So to hopefully I've intrigued you somewhat, and someone may come up with some work here at some point. So thank you all for listening, and I'll be happy to take any questions.
Okay, all right. Well, thank you for the excellent talk. Let me stop the recording now.
Yep.
So I'll do that.